The next step in learning lifecycle is model building. Model building includes choosing a model for our task and also training it. Basically, model building is the construction of our model. Let's gain an understanding of the things to be considered to choose the right model for our task. An insight from statistical learning theory, a theoretical part of machine learning, is the no free lunch theorem. Now, what does it mean by no free lunch in this context? It means that there is no universally best model. There is not a single model that performs the best everywhere for every data distribution or data set. Some model may perform well on spam filtering. Some can perform well in recognizing the images of cats and dogs, etc. It is quite important to keep in mind because it means that if we have someone that says to us, we should definitely use this type of model for everything, it is not really true. Some models work well in some conditions, while some others work well in some other conditions. It also means that learning is impossible unless we make some assumptions on the underlying distribution of data. We need not to bother much in understanding it in detail. What matters the most is the idea that if we have a variety of distribution of types of data set and different models, some model may perform well on some data while others not so much. Here in the graph, we can see that the classifier 2 performs really good in the middle. That is a certain type of distribution of a dataset, but performs badly on the rest. While classifier 1 performs generally alright for everything. So we can say that classifier 2 performs a lot better in the task that it is defined for. This basically means that we can have a model that performs good enough in all situations, while some other models are better in certain situations. Let's see some practical advice now that we may find useful. One advice here is that we can find some empirical guides that can help us to decide which machine learning models to choose for which tasks. These are not proven in theory, but they are really useful. This flowchart here is provided by scikit-learn. Scikit-learn is the main library for classic machine learning in Python. It's my advice to pause here to observe and read it more carefully and to gain more insights. Just to get it started, if we traverse from the start node, we need to ask ourselves if we have more than 50 examples or data points in our dataset. If yes, then we can continue. Otherwise, if it is suggested to gather more data, as we need a minimum amount of data to be able to learn. Then if we traverse further, it asks if we want to predict a category or not, and so on. Here the tasks have been divided in categories. The tasks that we have here are classification, clustering, regression, and dimensionality reduction. This chart can come in handy when we need a decision on the machine learning models that we have to choose as per the task that we have to perform based on the requirements that the task may require or the state that we are in. Again, it's my advice to pause here and go through the chart thoroughly. Let's talk about a few more suggestions. Another suggestion is to select a model depending on the criteria that we care about. If explainability is the criteria, then maybe use a decision tree or some more complex and powerful models. We need to take care of how much examples and features do we have, as some models perform much better if we have a lot of features and examples. We need to ask if we have a non-linearity in our data. So it means that if we expect the labels to be linearly correlated with our features, and if we plot our features and our labels, can we draw a line between the two, or does it have any other shape? The reason to ask is because some models take into account the linear dependence of the data to learn and further improve their performance, while others don't and prefer non-linearity. Another question to ask is computational complexity. What is the computational requirement of the model for both the training as well as for prediction? Also, do we require a certain prediction speed? If there is a specific requirement that the model has to make predictions within milliseconds or even less than that. Usually, models do not require much prediction or inference time, but it's something to think about that suits the best as per the requirements. This goes without saying that we should choose a model with the best performance, but the performance should be evaluated using cross validation. We will talk about cross validation in detail later in the lecture, but cross validation should be kept in mind. We shouldn't forget to tune hyperparameters for our models. We talked about hyperparameters in our previous lectures where we considered the depth of the decision tree. If we take a default value provided by our machine learning library, there is no definitive answer if this is the optimal performance and that can be gained by the model. To tune hyperparameters, we have different strategy. We can have a grid search where we put all the hyperparameters that we want to tune with their possible values in a grid representation. So the model takes one combination at a time, traverses the entire grid, and selects the best possible combination. We can also use random search method where the model randomly combines the hyperparameters with the available values to see which combination provides the best performance. And in addition to these, many other strategies that can be used to tune hyperparameters. Let's try to devise a model building strategy. What are the strategic steps that we can follow as a part of a model building strategy? To build the model, we start with the metric P, performance metric. This metric measures how good the performance of our model is. We can shortlist possible learning algorithms or model types that we can think to use. So we can say that for this particular task, we can use decision tree or neural networks or random forest, etc. In the next step, we chose hyperparameter tuning strategy. This is what we just talked about, that is to use grid search or random search or any other strategy. Then we pick a learning algorithm among the shortlisted candidate algorithms. Example, we decide to use a decision tree or any other that we found suitable. Then we apply each combination of hyperparameters to the tuning strategy. Let's say we train a decision tree with a depth value of 8. In step 6, we train our model. We use the training set to build the model using the algorithm and the hyperparameter values. Let's say we train our decision tree with a depth of 8 using the training set. Later in the lecture, we will talk about dividing our data set in training, validation, and test sets. The idea will be to train the model using a training set and to use a validation set to compute the value of our matrix for the model that we choose to use. Then we evaluate if it is our model is good enough. Um, if not, then we look for any untested hyperparameter values that we want to try to see if it improves the performance. To do so, we can pick another combination of hyperparameter values and train the model again. Let's say this time we want to train a depth of 20 for decision tree. We repeat step 6 and 7. Once we choose which model suits us the best according to our metrics, let's say we may seem the depth of 20 provide us with much better accuracy. We'll choose the decision tree with the depth of 20. Now we can try to repeat the same process with other models. Let's say we try random forest this time. So we can tune this hyperparameters of random forest and see what performance we get. Once we are done, we can probably try this time with neural networks and repeat the same process. In the end, we can compare the models to see which one performs the best as per the chosen matrix. Now, let's come back to the machine learning project lifecycle and see the next step in detail. Now that we understand the important step of model building, let's see how to evaluate a machine learning model for its performance.